To understand the graph theory, we will consider another chessboard that will be considered of 4 into 4 blocks. Previously, we have considered the chessboard that was 3 into 3. In this 4 into 4 chess board, the 4 corners of the chessboard will be removed and the remaining blocks will be considered for the further consideration. So in this diagram, we can see that this is the 4 into 4 chessboard, but we can see that the corners, 4 corners of this chessboard, they have been removed. Now we have, in the previous slide, we have asked question in the 3 into 3 chessboard. We will again ask a question in the 4 into 4 chessboard, that can a horse or a knight means horse, can travel around this board, pass through each square exactly once, and can return to the same square it started on. So this is the question of this 4 into 4 chessboard. So in this figure we can see that rather complex graph with 12 vertices and 16 edges, revealing all possible knight moves. Similarly, we have seen the possible moves in the 3 into 3 chessboard. Now we can see all the possible moves in a 4 into 4 chessboard. So these lines corresponding between the two vertices, they indicate that if the horse is at position number 3, for example, it can move to position number 2. From 3, it can move to position number 9 to 11, and if it is at position number 1, similarly it can move to 7, 6, 9, and so on, we can see in this diagram. However, the rearranging the vertices reveal the cycle that describe the correct sequence of move. So we can see here that there are 12 vertices starting from 1 and ending to 12. First, we convert this into the cyclic graph starting from 1 and ending up to 12. Now we will convert this checkboard into a cyclic form that is represented here in this one. Now we will see that this checkerboard, if we consider that the horse is at position number 1, that is here at position number 1, it will first move from 1 to position number 7 here, and we can see here it can move very easily from position number 1 to position number 7. So it is at position number 7. Then from position number 7 it can move to position number 12 here. So from 7 it will move to position number 12, and from position number 12 it can move to position number 6, that is from here it will move to position number 6, and from 6 it will again come to position number 1, that is the original position of that horse. So we can see that this is in the cyclic form. It can also be a cyclic form if we consider the horse is at position number 3. From position number 3 it can move to position number 2. This is position number 2. From 3 to position number 2. Then from position number 2 it can move very easily to position number 10, and here it can move to position number 10. From 10 it can go to position number 11. This is 11, and from here it can move to position number 11, and from 11 it can move very easily to position number 3, that is the starting position of the horse. So again we can see that this is again a cyclic. So we can use this cyclic, and we have proved by using this chessboard that the horse can move in a cyclic form, and it can use only one block only once, and after using that blocks it can reach to its original position from it has started moving. So the number of edges incident to a given vertex V is called the degree of the vertex, and it is denoted by d into V. For example, vertex 2 in this figure has degree of 3, while the vertex 4 has a degree of 2. Sorry, this is the vertex 2, and we can see that it has a degree of 3 vertices. It means that this vertex 2 is connected with 3 edges. One is connected with 10, second is connected with 8, and third is connected with 3. So this vertex 2 has a degree of 3. Similarly, vertex 4, this is vertex 4, it has a degree of only 2 because it is connected through these edges to only 10 number vertex and 12 number vertex. So it has the degree of 2 only. So the sum of the degrees of all 12 vertices, we can see this is starting from 1 and these are 12 vertices. In this case, there are 32 degrees, and in these 32 degrees, 8 vertices, namely 11, 3, 2, 10, 12, 7, 1 and 6. These 8 vertices, they are connected by 3 other vertices. So it means that these 8 have a degree of 3, and the remaining 4 vertices, they have the degree of only 2. So we can see here that there are only 16 vertices. For example, we can see here that 5 and 11, they are joined together through edges, and we can see this is 1 vertex, second edges 3, 4. There are 12 edges that are joining the 12 vertices, and the 13th vertex is between 11 and 10, and 14th is between 3 and 2, 15th is between 7 and 1, and the 16th is between 16 and 6. So there are 16 vertices that are present in between. But when we consider individual vertices, then the edges will be doubled. So instead of 16, the vertices will be 32. So it means that in any of the cyclic graph, the number of vertices will be twice as the number of the edges in the graph. So this is not a coincidence. It happens in all of the graphs. So in this graph, G with the vertex set V and the edge set E, we can say that this is the summation of V is a subset of V, and we have a dV because dV is the degree of the vertices, and the degree of vertices, that is in this case is 16, but when we calculate it will be equal to 2 times to 16. It means it will be multiplied by 2 and it comes out to be 32. So indeed an edge connecting vertices V and W is counted in the sum, that is summation V is subset of VD, and it will be the twice the number as we have seen earlier. First in the term dV and again in the term dW. So it will be twice first dV and then the dW. So the equality summation dV is equal to 2 and E, we know that the set of the edges. Explain why we cannot connect 15 phones in such a way that each is connected to exactly 7 phone sets. And we can also explain that why a country with exactly 3 roads out of every city cannot have the precisely 1000 roads.